Some say that climate change is the fight of our generation, and they wouldn't be wrong. Especially because climate change is evolving at such a rapid pace. Droughts have been at the forefront of the disasters caused by climate change. According to NOAA's National Center for Environmental Information, from 1980 to 2019, the total cost of damages caused by droughts exceeded $230 billion US, not to mention the lasting impact a drought poses towards agriculture. Without accurate metrics to foresee droughts, we cannot prepare for these events and allocate resources effectively. Today, my partner Stanley and I will present a project using convolutional neural networks to accurately predict the severity of a drought and when it may occur. Currently, labeling foliage quality is done by hand, with photographers taking images of the ground to be labeled. Though satellite imagery has been proposed for drought predictions, experts still use ground images to predict foliage quality, which is a key indicator of the drought severity and length. This requires a team to photograph many different locations. In addition, existing systems and models cannot predict droughts reliably. For example, they do not distinguish between edible plants and inedible ones, such as cacti, which make a huge difference for foraging animals. To surmount these challenges, our model has 10 different channels per image. There are 3 bands in the visible light spectrum, the red, green, and blue channels. But NASA's Landsat satellite takes pictures that are outside of the visible spectrum as well. For example, the infrared light spectrum is very useful for measuring edible vegetation levels. Human analysis of these channels simultaneously is extraordinarily difficult, and existing labeling is done largely without them.
Our model predicts foliage quality on a 65 by 65 image representing a 2-kilometer area. It can classify foliage quality into 4 classes based on the number of cows which can graze on it. A similar model trained on the same dataset is currently deployed in Kenya, where it provides index insurance for families and pastoralists. This model is currently letting shepherds in Kenya know which part of their land is most suitable to graze on, provides insurance rates based on index, and predicts drought severity through surveying the foliage quality of massive swaths of land. However, there is a huge catch with this model. It's only about 67% accurate. Furthermore, the current model used is less deployable and less easy to use, requiring a GPU. This poses a serious issue as companies, pastoralists, and age groups cannot effectively detect the severity of droughts and gauge foliage quality. Yet, droughts are the second most costly disaster, only being exceeded by hurricanes. Therefore, a more easy-to-use, portable, and robust solution is needed. Our model has 3 main advantages compared to the existing solutions. Firstly, it can survey a large area extremely quickly through satellite imaging, which itself is faster than ground imaging. Let's say we want to survey a 200 kilometer by 200 kilometer area of land. Ground surveying would require sending photographers to every kilometer of land, and then the resulting thousands of images being analyzed by a professional. Our satellite images are about 2 kilometers by 2 kilometers cropped. This means that we would need 40,000 images, cropped from larger images, to cover the entire area. Hand labeling 40,000 images is extremely infeasible, with large costs and time required. However, our model has a latency of under 15 milliseconds, meaning that 40,000 labels could be inferred in just about 10 minutes. This means surveying large swaths of land is feasible, and can make monitoring a drought much easier. Secondly, our model is about 10% more accurate, and much smaller compared to existing solutions. The increased accuracy can mean everybody is better prepared for the next drought. Finally, it's deployed on a web app, and offline it can run on slower hardware, even a 10-year-old laptop with a dual-core CPU and 500 megabytes of RAM. As a simple, easy-to-use web application, it just works, whether you're on your phone, your laptop, or even a smartwatch. All the computation is being done server-side. You can try out our application at stanleyzheng.ca. What makes this possible? Recent advances in model architecture, notably EfficientNet, and clever data preprocessing. Our convolutional neural network was coded in Scratch with TensorFlow. No AutoML here.
Using convolutional neural networks provides us with the most accurate way for aid organizations to prepare for a drought and allocate resources more effectively. These events cannot be prevented from happening, but using neural networks and machine learning, we can prepare for them in advance and mitigate the impacts by testing the quality of the foliage and directing shepherds to more fertile pastures to graze on. Moreover, our model can aid in future research and find new data useful for future drought prevention. Our model provides a gateway to the future. It proves what's possible, and it provides an outlook on how computers can benefit the world. Our model currently beats working models used for index insurance in accuracy, and is easier to use and more deployable. Of the nearly 700 imaging satellites currently orbiting the Earth, only one of them needs to take a picture, and that one picture could shape what tomorrow's drought looks like.